Well, again, welcome everybody. Thank you for joining Decarb Healthcare. We're on workshop number 5, Thinking Outside the Grid. Decarbonization through hydrogen solutions, fuel cells, microgrids, your ingenuity, and so much more. This is an AIA accredited workshop, and therefore, as always, I want to share this screen with the AIA logistics. So Mazzetti is a registered provider with the American Institute of Architecture Continuing Education Systems. Credit earned on completion of this program will be reported to CES records for all AIA members. Certificates of completion for non-AIA members are available upon request. And this is for continuing professional education. And as such, I'm showing you this copyright notice. Okay. We have an exciting lineup for you today in thinking outside the grid. I wanted to just quickly put this in context. What we are doing with Decarb Healthcare is developing a guidebook to help healthcare decarbonize. There is a focus around natural gas and combustion, but we recognize that lots of different elements play into that scenario. We're doing this by ultimately creating a guidebook, but first we wanted to bring together this community of folks who care about decarbonization and care about healthcare to come together, explore new ideas, share our ideas, and together build the type of solution strategies, both technical and social, that will help us decarbonize. Stage 1 eventually will bring our thinking together and push it out in ways that will enhance your ability to decarbonize either your healthcare institution or how you support healthcare. We're so excited that you are a part of this journey. And I'm personally extremely excited about this topic. I'm excited because thinking with the grid and beyond the grid is kind of a mega trend in energy that's recognized across the world. And I think that our conversation today will lead to some really exciting insights that will help us move all of this forward. I'm also excited because we have a great panel lined up for us. You see their names on the screen. We have Jay Maiden, Eric Neimer, Jared Ciferno, Shailesh Vora, Tom Lucci, and Angelica Chow as our panel. And then we will bring all of you together. Today, we're going to roll a little bit differently, so we will not do breakout rooms. Instead, we will have a community of the whole house, if you please. And so we will together facilitate a deep conversation that identifies technical possibilities, as well as strategies that might help overcome other barriers. I'm hoping we achieve something remarkable together today. We have an opportunity to think outside the grid. Let's do it. We're going to start doing it simply by understanding the grid. And I'm so excited to introduce Jay Maiden. I will let him share his biography and particulars, but we're excited to have him representing Southern California Edison and sharing the path to clean power and electrification. Jay, the floor is yours. Jay, if you're speaking, you're still on mute. There you are.
There we go. I thought I clicked the right button. Troy, thank you very much. Full disclaimer, I am actually an HVAC and plumbing engineer. Most of my career in healthcare. Before I joined Edison, I'm with the Emerging Products and Technologies Group. And so we're the people who build test and lab test all sorts of HVAC and building ideas to more decarbonizing. It used to be kWh reduction, but now we're trying to decarbonize. And so that is my background. I've been with SE for 10 years now. And with that, if you could go ahead with the slide presentation, I'll give you a little bit of perspective from the utilities on what we're talking about today. And let me see, I am not, there we go, thank you. Can you go back up one slide, please? There, thank you. So this is just a general look at greenhouse gas emissions. And as you can see, the big part to get out of this one is that Mostly it comes, a lot of it that we address or that we're going to address today comes from that 12% commercial and residential, so burning natural gas at buildings, and the 27% that comes from electricity generation. The other ones are important too, but we're going to concentrate on those two today. Go ahead and advance. So this is Edison's pathway 2045 to get to zero carbon by 2045. This parallels a lot of the rules happening in California about having 100% clean power. And so what I want to really get out of this particular chart is not everything on it, but the first one, providing 100% carbon-free electricity by 2045, and then building electrification, 70% of buildings being electrified by 2045. And then the last one, because this gets into gas, biomethane. There are going to be times where you're just not going to electrify things. And for those, the overall strategy is that the natural gas we use, 39% of it comes from biomethane. So with that, if you go one more slide. So within our strategies, we took a few out. They're over on the right-hand side, but for here, again, 100% carbon-free electricity. Storage is a big part of that, solar, wind, obviously. Electrifying the heating, the water heating, and the cooking in the buildings. And we'll get into cooking as far as commercially during panel if you want to. That's been a very difficult subject for us. And then again, I talked about low carbon fuel. I threw in hydrogen in here, clean production of hydrogen. In other words, using non-carbon electricity to generate hydrogen as a fuel. So if we move forward one more slide. So the big question that came up when I was putting this together, Austin at Mazzetti told me yesterday, well, what does this mean for us, the customer? You know, that's all nice, but how much is all of this going to cost? And this chart is kind of difficult to follow, but it's the best I could find really quickly. And what happened was in the utility industry, the California Energy Commission and all that, they studied, well, what if we took a path of no building electrification and said, look, all our natural gas load is going to come from what we call synthetic natural gas, but biomethane, hydrogen, and that sort of thing. And so what it shows is if we went that wild path, you know, that, not wild, but that extreme, you could see where cost by 2050 would go up very high versus doing high building electrification and then taking care of what we couldn't with electrification using biomethane, hydrogen, and that sort of thing. So this sort of addresses that question of in the future. I know a lot of questions come up, and I remember designing this, I'm going through this now. It's like, well, we electrify the building and then it's going to cost us more in utilities and all that. This gives you a path of where that's going in the future. So it doesn't quite answer quite the question, but it helps out with a little bit in long-term costs for commercial and institutional and residential customers. So going on one more slide. So this was just giving an example of a building. Will electrification cost me more? There's a new medical office building in Santa Rosa, California, that was LEED Platinum, all electric, and the construction cost savings were actually $1 million. I have to find out how they're running as far as what they would have done had they been, as far as operational costs with natural gas and electricity, a mixed fuel building versus all electric. But to start off with, the construction cost savings were $1 million. So there are savings on just the first cost going all electric. Next slide. And so where is the utility involved with all of this? And how do we encourage building electrification? Well, really, the biggest thing we have is financial incentives for energy efficient building electrification. And throw in that word energy efficient building electrification, because we're still making this transition from you saving kilowatt hours to saving carbon dioxide generation. We don't want to go backwards in energy efficiency and have people put in, electric resistance water heaters versus, let's say, a heat pump water heater. So we offer, a bigger version of those rebates you see at Home Depot. We offer them for custom projects to provide energy efficiency, building electrification. We also provide design assistance and workforce education, because a lot of people on this call are the cutting edge of the whole building electrification or carbon dioxide reduction or greenhouse gas reductions. But then you go to the ASHRAE meetings, and we have the bleeding edge, the leading edge, and then we have the rank and file HVAC designers, for example, and trying to educate them, the contractors, the builders, and that sort of thing. So we're heavily involved with workforce education. And then with that, I think that was my introduction. So I'm gonna, unless I had one more slide, I'd turn it back to you.
Great, Jay. Thank you so much for that presentation. You can hear that even the grid is thinking outside of the grid. We're going to extend that thinking a little bit further, but first I want to say a quick word on format. So again, you're going to hear from our panelists. If you have questions for our panelists on their specific topic, you can write them in the chat. We may be able to take 1 or 2 questions if they're specifically on that presentation. And then ultimately at the end, we're going to put all of this together in conversation. So as I say that, and as I give a chance if there's 1 or 2 specific questions to float up on our grid, I want to highlight that we're now kind of in the section of our presentation where we are thinking outside the grid. First, we're going to hear in what I would call a roadmap or a framework for how to think outside of the grid. Then we'll dig into technologies on hydrogen and fuel cells and deal with some of the things that have come up in our other workshops. And finally, we'll have a case study of a microgrid that is being designed right now. We'll use that case study to dive into our questions. With no further ado, I'm going to introduce Eric Neimer. I'm going to take just a minute to introduce Eric because he is humble and because I've had the privilege of asking him to do a whole lot of difficult things over the past year, and I'm able to ask him to do those things because he is both an electrician and an electrical engineer. And so he wears multiple hats and brings different perspectives. And because of that, I've been able to reach out to him as a technical expert on many different things. And so I'm excited to introduce Eric, who is going to, in some senses, give us a framework for how we might think about microgrids in healthcare as we think beyond the grid. Eric?
Sure. Thanks, Troy. That's too kind, I think. I lean into Troy probably more than he leans into me. But that being said, what we wanted to do here, Troy's right, is kind of lay out if you're thinking about a microgrid, if you're thinking about how can I bring this to my clients or my jurisdiction, some of the items that you really need to be thinking of, kind of the 1, 2, 3, 4, if you will, some things that you want to have in the back of your head to be thinking about, all not necessarily linearly, but in conjunction with one another. Full disclosure, this actually started out as the challenges to microgrids was going to be my part, and it got a little Debbie Downer. So I'm more of a glass half full kind of guy, and I felt like today's challenges are really just tomorrow's opportunities. So we'll go through these kind of the challenge and then what opportunity that actually presents us in the future. And with that, I'll hit the first bullet. Education. We have been designing healthcare systems with normal power being the utility and the emergency power being diesel for 100 years. I don't know that there's anybody on this call who doesn't remember doing it that way. Tip of the cap to you, and I want some of your experience if you'd like to talk after, but I don't think anybody knows a diesel generator and I lost my slide. Pre-diesel generator and normal utility power setup. So a lot of what we're going to do here is we're going to have to be rethinking about what does that even mean? What does normal mean? What does emergency mean? Does it matter? Is it really just power source 1 and power source 2? If we're talking about potentially having our, let's call it normal or power source 1 power source on site via a microgrid, then we're talking about having the utility play the backup role. And what does that mean? And ultimately, before we get into working with the utilities, is if you talk to mission critical folks, they'll talk about nines. And what does that mean? If you're a 2-9 facility, it's 99.99% up. Is your facility has power. So if you think about the utility and how often it is online, that potentially being either a shared or backup source, we're talking about an extremely reliable and resilient system for your healthcare facility. The other part of this is just generic, is if you went and asked 10 people what a microgrid was, I think we've had people tell us they thought just CHP was a microgrid. Other people will think that means solar and batteries or fuel cells. And what does that even mean? And just some of the things you want to start thinking about initially as you look at these types of projects. And now the next one up is going to be financial. And because the money is money talks, right? There are some expenses certainly associated with instituting a microgrid. Right now, some of the technologies are newer, and with any new technology, there's potentially a higher ticket. The good news is that, like many other technologies, the longer they're around, the cheaper they get. So we are seeing exponential decreases in the costs of photovoltaics, battery backup storage, fuel cells themselves, the controllers for the microgrids, all the pieces and parts, the more we see of it, the cheaper it's getting. And depending on what type of facility you are, you may or may not be interested in tax incentives. So there are federal, state, local incentives, whether they're taxes or rebates, things to be thinking about. And even if you don't want to have the initial cap expenditure to institute a microgrid at a facility, there's ESCOs, which are energy service corporations, who will come in, they'll buy the equipment, they'll install it, and then you just pay them. Or a PPA, very similar, power purchase agreement. They work very, very similar, and there's a lot of those financial incentives and programs out there. And moving on to the next. So this is, this is probably I think this is the biggest challenge, but it's also the most exciting one. We are here to talk about decarbonizing healthcare, and a fuel cell right now, which you'll hear more about, is primarily a natural gas powered piece of equipment. But the shift to hydrogen and the potential for retrofitting fuel cells to hydrogen fuel source as their primary fuel is enormous. It's just such a big deal to think that we could be using hydrogen to power hospitals or homes, for that matter, that we can go not just incremental, but huge drop off in carbon footprint and usage of our facilities. So the other part is, how do we get hydrogen? We can't or I should say, there's some popular thought out there that we can just swap natural gas lines and start pumping hydrogen through them. That's not going to work. We have to think about how we get hydrogen to the site. Do we store it? Is it trucked in? Is it on a cycle? But these are just things that we want to be thinking about, because even though it might be hard to get that hydrogen infrastructure in place, that is a game changer for decarbonizing our healthcare facilities. And the next one, because I think I'm going long, is so as we approach the microgrids, sorry, I get really excited about microgrids. So they only gave me 5 minutes, and I'm trying to stay as short as I can. But is some of the people, there's so many different hands in this: codes, local AHJs, utilities, different states adopt different codes at different times. And right now we're actually working with the committee on the NEC code making panels to rework the microgrid language so that it's more viable from a code and AHJ perspective on its flexibility and inclusiveness and how we can deploy it on site. So there's the potential to be working with the utilities because they're not in the business of not selling power. And if they become a shared source or a backup source, we want to be talking to them early and often about what that means for them and how we work together. And of course, the AHJs need to be comfortable, and that ties back into the education and potentially re-education of what they've seen, what they understand. If it's new, some people don't like that, it's change. And with that, I think I've probably gone over time, and I will send it back to Troy.
Excellent. Eric, thank you so much for that presentation. As I check to see if there's any questions that we need to address, I just want to highlight this framework and this opportunity to think beyond the grid. It's amazing to think about the trends that are coming together, right? The global trend of distributed power, getting back to distributed instead of centralized power. The need for resilience is especially seen in California. The worldwide desire and impetus to decarbonize, and movement around different paradigms that are helping us to create a moment where microgrids, especially for healthcare, might be really powerful for a use case that already needs to think about emergency power and has some agency and some understanding of what different sources of power means. It brings us to the opportunity to have some optionality around how we can move forward. And so as I wait to see if I'm being sent any specific questions, I just want us to think about how this framework will play out and how we might think about hydrogen and fuel cells and distributed wind and other frameworks for energy in the context of a microgrid. All right, so we are going to move on. So I am excited to introduce Jared Ciferno, who's going to talk to us about the hydrogen economy. I will let him give a deep introduction for himself, but Jared, go ahead and take it away.
Well, good afternoon. You can hear me okay, Troy?
Yeah, I can. Thank you.
Okay, great. My name is Jared Ciferno. I'm the technology manager of the upstream and midstream oil and gas program. I work out of the National Energy Technology Lab. I'll show you a slide in a minute. But we are one of 17 national labs under the Department of Energy's National Lab System. Our primary focus is fossil energy research and development. And so the topic here today is really near and dear to our advanced research programs. That's what I'll discuss today. I have about 20 years experience in advanced fossil energy technology research. Did you want me to share my screen, Troy, and go through a set of slides?
Oh, yes. You can go ahead and share your screen if you like.
Okay. This is the overall national lab system. NETL actually has 5 locations: Pittsburgh, Pennsylvania; Morgantown, West Virginia; and Albany, Oregon; and a few other offices in Alaska and Texas, Houston. But bottom line, we're a little bit different than the other labs because one is we're completely focused on fossil energy, and that really ties into the hydrogen and really deep decarbonization. We're an applied national lab. We do research on site. We also have a large project management program that we do research and technology development with industry and academia. Our portfolio is roughly $1 billion a year that we invest on advanced technologies. Let me just go. So I'm going to talk real briefly today over a few minutes on making, moving, and using hydrogen today. Where are we at? And just give you a sense of the challenges that the DOE is working on. And it's not just NETL, it's actually a lot of those national labs across the system here has a lot of ties into decarbonization and hydrogen. So it's NETL was one piece, Office of Fossil Energy. But also you heard of the National Renewable Energy Lab. There's a lot of other key players. The good news is hydrogen is not new. It is generated throughout the United States with 110 or so facilities of different sizes. So we know how to generate hydrogen and we know how to use it. And it's distributed. So that's the good news. This next slide gives you a sense of how much are we using today, what sectors, and a couple of key takeaways. And this is million metric tons, and we're using around 11.4 million metric tons per day today. But look at the sectors that hydrogen is being used in: refining, ammonia, fertilizer, methanol, metal processing. These are high value products. So again, technology is available today to produce hydrogen. Primarily, it's from natural gas that's abundant, low cost, and it's used typically from steam methane reforming. So the good news is we have experience today to get up to this level. But one key takeaway is this isn't power generation. I mean, these products are high value, and so there's a lot of latitude to overcome the cost of hydrogen separation. When you look at projected increases, whether it's the EIA or other resources, they can come out at 16 to 50 million tons per year. Again, you'll see a lot of projections out, and really that depends on a lot of factors of decarbonization taxes, future regulations, the acceleration of advanced technologies, and can we even have a safe integrated system? But when you look at where are they projecting beyond today's markets, really power, as we mentioned earlier, transportation is a big deal, as well as residential and industrial. What can we do to try to facilitate this decarbonized fuel? So when you look at those projections out into the future, this is a little bit busy. You may have seen this type of slide, but on the left-hand side, it shows you our power infrastructure, electricity generation, whether it's from renewable resources, nuclear or fossil. And so on the left-hand side is your electricity, your power. And on the right here is your hydrogen and the uses of hydrogen, a diverse set of hydrogen uses on the right-hand side. So essentially, nuclear can either generate power directly, or you can use the power if you follow around a semicircle. Can you use part of nuclear to generate hydrogen through electrolysis? Is an advanced technology. What I'm going to briefly talk about is fossil use, whether it's coal and primarily natural gas with carbon capture, utilization, and storage. Why is that important to really consider? One is because we do it today. Easy answer on fossil sources, natural gas to hydrogen. But we have an abundant resource in the lower 48. It's very, almost 3,000 TCF of natural gas. It's low cost, easy to get to. And we have an abundant CO2 storage. So it's actually really spread out throughout the United States. The DOE has stored thousands of tons of CO2 in the last 10 to 20 years of advanced research programs. So these are some advantages as to why the fossil resource, we're taking a heavy look at it as part of a portfolio. So one takeaway is there's not one best-in-class hydrogen generation source. There are a lot of advancements made. We are doing it today. And again, there's not the best in class of hydrogen use. There's a lot of various opportunities to use it. So when you look at today, I mentioned several times we're doing it. The primary hydrogen generation today is steam methane reformer. Real simple, but again, your methane stream coming in. These are catalytic reactors that operate at high temperatures, high pressures. And then you have to separate the gas after to generate a pure hydrogen stream over to the right. The key takeaway here is so that today's technology is good, steam methane. It's been developed very well by industry, and it does well with its high value products. Couple key takeaways. You can notice here, this is a simplified diagram, but a lot of unit operations here. Catalytic reactor, you're doing separations. And to really get low decarbonization, you need to add CO2 capture on several areas. You're paying the price on capital investments and energy penalties every time you added unit operation. So that's why we see a lot of value in advanced technologies to generate hydrogen from fossil. What do I mean by that? So we're looking at transformational hydrogen production, but really to simplify it, it's really to try to take a direct approach where you want to use advanced catalyst systems, we call multifunctional catalysts, that will separate, that will convert the methane, even if it's not methane, but methane, ethane, propane, other higher molecular weight liquids or gases in the natural gas, but convert them in one step over into hydrogen or solid value carbons, nanocarbons, as well as high value liquids. This is really co-production. This is just a simple set here of these advanced technologies and versions. A lot of progress has been made in the last few years. We still have a long way to go, but bottom line is this box here is focused on decreasing the energetics for the system, trying to use process intensification where you're going to combine the reactor and the separator in one box. And you want to use catalysis in your favor. We have technology today, nanotechnology and engineering approaches that enable you to simplify this multi-step process really into a one-step process. These are just some visuals over to the right where I'll just show you the one on the upper right-hand side where you're coming in with methane through propane and you're doing a separation on high-value benzene and you're generating hydrogen at the same time. And the catalyst works as a cage and it does this separation. Very advanced technology. You can see plasma, electrochemical, microwave. We're trying to provide different energy inputs to energize the catalyst at very low energy use. That's the key takeaway. One step, very advanced technology. That's on production. That's what the DOE is working on, one snapshot. When you look at the existing infrastructure, we have a good understanding of our infrastructure today. It's aged, it's old, but we have 2.4 million miles of pipeline. Can you transport hydrogen or blends of hydrogen? Is that doable? You have 2,000 compressor stations. It's aged. Compared to our experience of just pure hydrogen pipelines, 1,600 miles versus 2.4 million miles of natural gas pipelines. Significant difference in terms of our experience. This pipeline system in the US is not a perfect system. It does leak methane. When you start adding hydrogen into it, the technical challenges even are elevated even further. So what are we doing there? This is just one project where we have 6 national labs have partnered with 20 industry and academic partners over several years. You might be familiar with this project. It's $15 million over a 2-year period. Their focus is on looking at advanced 3 areas, looking at the existing pipeline infrastructure and the materials, and really assessing would it be conducive to transporting hydrogen, depending on the material sets, and look at the life cycle emissions. And then what kind of advanced sensors do you need in leak detection? Leak detection for methane was trying to detect methane, but could those same sensors work for hydrogen? So this is one project where we're looking across the infrastructure very fast to get a sense of, can we transport it? What concentration? Real quick, I know a lot of mechanical engineers from your firm are on the phone, but compression is not free. This is just a figure of mole fraction of hydrogen, 0 to 100%. And this is your power supply on the y-axis. And this is just a simulated of the age of the pipeline. You can do a roughness factor. The key takeaway is due to the volumetric flow rate and the density, the characteristics of hydrogen versus methane, you're going to pay up to 5 times the compression power to move it. So the key takeaway is, does it make sense for large central hydrogen plants or small distributed hydrogen plants? We're talking about microgrid. But again, that's where the DOE is really looking at advanced technologies. We're used to economies of scale, large plants. That may be more conducive due to this energy penalty of moving the hydrogen, that may be more amenable to looking at small modular hydrogen generation systems. Very important. Lastly, storing it. A lot of subsurface storage is not new. Surface storage is not new, moving it, high pressure vessels. A lot of research. We have a significant amount of information and experience storing natural gas throughout the US. We only have one commercial subsurface hydrogen storage facility, 2,500 metric tons in Texas. So our experience there is much less. So a lot of unknowns are out there, and we have some sense of it. The challenges of, can you store the hydrogen? What's the fluid flow behavior? What is the uptake? But what is the microbiological impact? When you put a blend of 30% hydrogen down in the storage, are you going to get 30-70 back? You're going to have buoyancy issues. How do you control that? So again, we're trying to fast track the research in this area. What does the future hydrogen market look like? can you store it? What do we have available within the United States? That is really critical in addition to the pipelines. So that's brief. Thank you for the 5 minutes, but those are the 3 segments we're doing under oil and gas that we're focused on with the other Department of Energy areas. Thank you.
Okay. Jared, thank you so much for that presentation. I'm going to take the opportunity of being the host to ask some what might be 101 type questions. So Jared, for our audience, for the sustainability director or the facility manager at a hospital in California, can you give your estimation of when hydrogen will make it to the hospital? So kind of on the timeline, when do you think we'll get hydrogen on site in a way that a hospital might find useful? And obviously you don't have a crystal ball, so you don't know
No, we don't.
your assessment.
One key driver is, one goal of the DOE is really by 2035 of having significant.
Hey, Jared, I'm really sorry to interrupt you. It's a little bit hard to hear you. Can you just lean into your mic a little bit more than you typically would?
Right. So can you hear me now?
I'd say even louder.
Okay. So back, it's by DOE has an aggressive timeline by 2035. Really a function of when is the hydrogen going to be available. Is really a function of regulations and policies. That's one part. Whether as well as industry on decarbonizing the gas. So I would say when you look at that figure, a lot of projections have increases in industry use, which would be hospitals, large commercial use by 2030. It's probably a good gauge for that. The good news is it's not that you don't have technology to generate it. You can, as I mentioned. And they're trying to fast track lower cost technologies. I think we'll know in the next 5 years, can you transport it and can you store it? That's the key part. And what's, as well as what are the intermediate enabling technologies? Some downstream units, but it can accept 30%. Some can only accept 5%. So that's the key challenge of if a hospital is dependent on hydrogen, what concentration of hydrogen? Is it a dedicated hydrogen pipeline to the hospital system? Or can they, what are the opportunities to tap into a pipeline that has a blended hydrogen? I don't know that, Troy, I'll be honest. The bottom line is we have multiple departments looking into that and fast tracking it as fast at an accelerated pace.
Great, excellent. One more really quickly. What about on-site development of hydrogen via electrolysis, or is there opportunity to create hydrogen on site with, say, energy from solar? What's the thinking around that, and how might that be useful for hospitals?
Yes, that would be, because as I mentioned, your energy penalty to move the hydrogen, beyond just compressing it, but you have leakage. It's much more difficult to keep that within the pipeline system. So there is a look into modular systems, hydrogen, small electrolysis. And I think the National Renewable Lab has multiple.
I don't even know where this came from, but.
Yeah, absolutely. The small hydrogen production is a very high interest, yes, on site.
Great. Jared, thank you so much for that presentation. For the faces I can see, I can already see kind of your minds whirling. Hopefully we'll put some of these together right after we hear about hydrogen fuel cells from your DOE colleague, Shailesh Vora. So Shailesh, why don't you go ahead and share your screen, give yourself a deeper introduction, and then tell us about fuel cell R&D.
Can you hear me? And can you see my screen? I'm not sharing yet, but can you see my screen?
We can't see your screen quite yet. We can hear you.
Okay, now can you see my screen?
We can see you, Shailesh.
But you cannot see my screen? Nope. Troy, I sent you the slides. Can you share?
I can. Why don't you get started, and I'll get it up your screen up as soon as I can.
Okay, that's better. Okay, my name is Shailesh Vora. I am Jared's colleague. I am the technology manager for the solid oxide fuel cell program at NETL. We are based in Pittsburgh. I've been with DOE about 11 years. Prior to that, I was at Westinghouse and Siemens, both in the fuel cells area here in Pittsburgh. So next slide, please. Okay, I'm going to talk, just give you a fuel cell 101 first. I'm not sure if everybody's familiar with fuel cells, and there are different kinds of fuel cells and so on. So what I'm trying to show here is, basically start with what's a fuel cell. Fuel cells are basically energy conversion devices. They convert chemical energy of a fuel into electrical energy, and it's a direct conversion. There is no mechanical energy conversion in between. So fuel cells are highly efficient. They are also modular, meaning you can design your fuel cell system to fit your need in terms of rating. You could have a small, let's say, a 10 kilowatt fuel cell system, or 100 kilowatt, or a single digit megawatt, or tens of megawatts. So the fuel cells are modular, and they are characterized by the electrolyte. So there are different kinds of fuel cells. So you may or may not have heard of molten carbonate fuel cells, solid oxide fuel cells, fuel cells based on polymers. They're called PEMs. So these are characterized by the electrolyte, and so depending upon what the electrolyte is, that's the fuel cell. What we are working on, the Office of Fossil Energy, is the solid oxide fuel cell. These operate at high temperature, 700 degrees C or higher, and they have basically a ceramic construction. The low temperature fuel cells are also being worked on by DOE, and that's the Office of Electrical Efficiency and Renewable Energy, EE&RE. They are working on the low temperature fuel cells, which are mostly used for transportation applications. They're also used for stationary power, but primarily transportation applications. The phosphoric acid fuel cells, as well as molten carbonate fuel cells, they're considered somewhat mature in technology, and DOE does not support these fuel cells at this time. So I'm going to talk about solid oxide fuel cells, primarily for stationary power applications. A fuel cell system can be viewed as three parts: the cells itself, like the Intel inside, the microprocessor. The cells run, that's the power block. Then what we call the stacks. So there are multiple fuel cells are connected in series and parallel, and depending on the rating, you could have hundreds of cells, thousands of cells, or tens of thousands of cells, and that constitutes a stack. And then there's this balance of plant, which is the auxiliary equipment, the air supply, the fuel supply, the controls. So all these three combined give you a fuel cell system. So sometimes people just talk in terms of fuel cells, which is just a cell. But what we are talking about is this whole system put together, which comprises all the electrical parts, the mechanical parts, and the electrochemical part, which is the fuel cell. So I just wanted to give you an appreciation of there are different kinds of fuel cells, and then when we talk about fuel cell, it's a fuel cell system, not the cell itself. Next slide. Okay, the objectives of the DOE fossil energy program are to validate small. So we are basically an R&D program. So where we will end up is a low-cost, reliable, first-of-a-kind fuel cell system. That's the objective. We are not making hundreds of systems which would then be used in hospitals or any other applications. What we are trying to work on is basic R&D to improve the cell technology, to improve the systems technology, and show the first-of-a-kind prototype. So our near-term objectives are to work to validate small-scale systems. When we talk about small scale, it's like tens of kilowatts to maybe a single-digit megawatt system. We are also working on electrolyzers. Just can I go to the previous slide? I just missed one point. Sorry. Yeah, here the fuel, basically the fuel is in and electricity is out. A typical fuel is natural gas, but hydrogen can be a fuel also. And when fuel cells are run in reverse, meaning when you provide electricity, you could then produce hydrogen. Okay, so and that process is called electrolysis. Next slide, please. So we are also working on small-scale electrolyzers, which would produce hydrogen on site. And so it's a distributed generation application. And we are also doing R&D to mature the technology, primarily to lower the cost and improve the reliability. Next slide, please. We are working in 3 different areas. The cell itself, so we are working on the cell materials, ways to produce a cell. Also, core technology, which is everything besides the cell, the interconnects which connect the cell, the insulation that goes because of high temperature, the high temperature operation that we have, and different system components. So we are working in all these 3 areas. We have about 50 projects that span all these three key technology areas. Next slide, please. The way we work is it's a collaborative approach. The DOE works with industry and tries to identify what are the problems that they would like to solve. And then we have projects from universities, national labs, small companies, and even system developers who then work on sponsored projects that are funded by DOE to lower the cost and improve the reliability of these fuel cell systems. TRL, the second sub-bullet, TRL 2 to 5. TRL stands for Technology Readiness Level, and it's a scale of technology maturity where TRL 1 is just a concept and TRL 9 is a commercial product. So we are working in the TRL 2 to 7 range, where 7 is really the first of a kind prototype. Next slide, please. These are our annual budgets since the year 2000 when we started in earnest. Our current budgets, annual budgets, are anywhere between $25 to $30 million a year. For example, in this year, we are the annual budget for fiscal year 21 is $30 million. Next slide, please. As I'd mentioned, we have about 50 projects that span across the country. Most of them are at universities, national labs, and what we call system developers. So this slide shows all the projects that are ongoing right now. Next slide, please. This is a snapshot of the whole program in one slide, and I can spend half an hour on this slide, but I'm just going to spend a minute or so. We started in earnest in year 2000, where we basically did not have any cell materials or cell design. So we spent almost a decade trying to develop the cell, establish all the cell materials for the anode, the cathode, the electrolyte, did some small single cell type testing. This decade, or last decade now, 2010 to 2020, we were building small systems. We were testing 5 kilowatt to 100 kilowatt type systems. Lately, we have now matured to 200 kilowatt systems, where we had a first of a kind test last year here in Pittsburgh. So, and our plans are to move to a megawatt into next 1 or 2 years. But this all will be, I just want to caution, this all will be first of a kind system prototype demonstrations. And then we would do 1 or 2 more iterations. And after that, we would leave it up to the developers to then further invest and lower the cost, further lower the cost, improve the reliability, and mature the technology. Next slide, please. Just showing the two systems that we tested recently. On the left is a 200 kilowatt fuel cell energy system. This is a fully integrated, remotely operated system. Two 100 kilowatt modules, has about 2,000 cells. Our target was to run it for 5,000 hours, which is about 6 months. The system degraded. The target was to have the system reliability or system degradation less than 1.5% per 1,000 hours, and the system met that. This system has now been dismantled, and we are doing post-mortem on it. On the right is a 10 kilowatt system that is more suitable for a data center type application or a residential application. This was manufactured by a company in the UK called Ceres Power. That was tested for 1,000 hours, about 6 weeks at the University of Connecticut. Ran well, and it says post for COVID-19. So it was stopped because the labs are closed in the university, and now it's opened again. So the system is on. So that's basically in a nutshell the program. I just want to emphasize it's R&D on different cell components, system components, and first of a kind system. Next slide, please, which is my last slide and takeaway. Basically, we are conducting R&D both on SOFC, meaning fuel cell, as well as electrolyzer systems. Trying to get fabricating experience on small scale systems, and we are well aligned with the cell development R&D is well aligned with the industry. Last slide is my contact info, and I'll be glad to take any questions. Thanks.
Great. Sailesh, thank you so much for that presentation and for sharing with us kind of the the research and development process. It's really exciting to see. Next, we're going to have up, just making sure. Okay, thank you. Next, we're going to have up Tom Lucci from Bloom Energy, who's going to talk about fuel cells from a different perspective. And so, Tom, the floor is yours.
Great, thanks so much. As the slide will tell you, my name is Tom Lucci, and I'm with Bloom Energy. I'm in product management, and I'm covering our kind of utility side as well as our hydrogen side at the moment. So thanks for having me chat today. Let's see, so we are Bloom Energy. Off to the right there, you see one of our installs at a Kaiser facility. We'll see more pictures of those later, but that's kind of what our production fuel cells look like. And it was nice to kind of follow Sailesh to get, the primer, if you will, about fuel cell 101. Some of this might be slightly repetitive, so but hopefully it will also drill some of the points home that he brought up. Next slide, please. So just kind of quickly, starting at the top left, it's clean, reliable on-site power. So there you see a bank of energy servers right next to kind of an outdoor dining area. So it is quiet, and there's no kind of emissions that you might expect from a diesel generator, including noise. We are on the New York Stock Exchange. We're proven technology, so at least 450 megawatts deployed. And then we manufacture here in the States, in California and Delaware. Let's see. Okay, so again, this might be slightly repetitive, but to Sailesh. But if you think about how the electricity is made, so to speak, on the top left, we've essentially got natural gas in, along with air in, and through an electrochemical process. Essentially, there's three things that come out of it, at least when you're using natural gas as a fuel source. You've got electricity off to the right. You've got water as an output, which can be recycled and reused by the system essentially, and then carbon dioxide. We'll talk more about the carbon dioxide in a bit, For now, it might, suffice to know that it is less carbon dioxide than, traditional generation systems from natural gas. What you see on the top right there is a 300 kilowatt block of what we call energy servers. So they're roughly, big refrigerator sized things that we line up next to each other. And it provides, that particular stamp, if you will, provides 300 kilowatt of essentially always on power. And then across the bottom, you see the hierarchy that again, Shailesh referred to, right? So you've got fuel cells, which you put in a stack, which you put in a server, which you put in a system, which you just kind of, add and add until you've got the capacity that you want. So, tens of megawatts are certainly relatively easy to do with proper planning. Next slide. So this is just kind of, I think a lead into the rest of the presentation more than anything else. So, typically, or historically, I should say, Bloom has kind of competed against the grid. A lot of it in terms of electricity costs. That was kind of one of the chief advantages that we could bring to our customers, is a lower cost of electricity using natural gas, especially obviously in the markets where the price of electricity was higher. So we're just at about 9 cents a kilowatt hour right now, and that's continuing to go down. But I think what this does is kind of talks to, how we got to where we're at versus a little less of where we want to go. We do want to reduce cost, but really just kind of saying we're going to compete against the grid on power, I think is kind of doing a disservice to what we can do for our customers and for, not to be too, grand, but help lower the carbon footprint overall, be a part of the solution. Because we can use hydrogen, for example, as a fuel source, which is essentially a carbon neutral fuel source, as again was previously described. So why don't we talk about those things next? Next slide, please. Okay, there's a lot on this slide. So I think first I'm going to direct your attention to the chart on the left. So the chart on the left, I think the thing to kind of break this down into, and this is the percentage of electricity generation from different fuel sources, even as you get to 2050, kind of on the right side of that, you're going to have about 50% of it from natural gas and coal, and roughly 50% from renewables and nuclear. So today, in the future, still, the natural gas will play a leading role in supplying the energy that we need. Now the graph, the chart in the middle there is kind of a breakdown of the renewable generation and how that's growing. And that should be pretty obvious, I think, right? So over time, solar and wind especially are really going to pick up the bulk of the load, if you will, of renewable generation going forward. Now, Bloom is in a neat spot, in my opinion, and this is one of the things that I find that's exciting about the technology, is that we can play a role in both sides of it. So although one fuel source is natural gas, and that's kind of the classic fuel source for fuel cell, it does emit carbon dioxide. And of course, we'd like to not have carbon dioxide in the atmosphere. So one thing that we can do, if you look on the bottom right, is also ingest biogas and hydrogen, or in varying percentages, in order to lower that carbon output and use more carbon-friendly fuel sources. The technology is essentially the same, and I'll talk about that a little bit more next. But I think it's important to both acknowledge where we're at today in terms of a natural gas and carbon-based kind of fuel sources, and where we're going tomorrow as well into renewable fuel sources. And kind of when we talk about the hydrogen economy, we're really getting into the future of things versus today, where we're a little more reliant on carbon-based sources than we'd like to. Why don't we go to the next slide? So this is a fuel cell. Is there a build here, or have we got partial? Okay, this might not have come out right. I apologize for not proofing that. So, but in fuel cell mode, if you look up top, Before I showed you what what natural gas looks like as a fuel source. And as natural gas is a fuel source, as I mentioned, there's some carbon dioxide out. Here in, if we're just using a fuel cell mode, if you will, and putting in hydrogen, essentially you get electricity out and no carbon dioxide. That's some of the text that's missing from the right there. So essentially, there is no carbon dioxide output from using hydrogen as a fuel source, and it uses this fuel cell technology. Now, again, as Shailesh indicated, if you can kind of reverse this, essentially use the same technology to put electricity and water. Here we show it as steam in the bottom right, but electricity and water in some form back into the fuel cell, that same technology, the solid oxide fuel cell, and essentially you get hydrogen out. So this is, very much a, kind of a reversible technology theoretically. There's of course some differences in how they're done underneath the covers. But from a broad spectrum perspective, you can take hydrogen in and get electricity out, or put electricity in and get hydrogen out. And this allows us to fill a few different roles going forward. Next slide, please. So this is, I hope, kind of a higher level picture, and maybe a good one for me to end on here. So if you look on the left, you see, some classic green renewable energy resources like wind and solar. And as we all know, there are times where they're generating more than the demand requires. And in those times, you can actually use that electricity to go into an electrolyzer to generate hydrogen along with water. And then that hydrogen essentially turns into energy storage, if you want to think about it like that. And then that hydrogen can be used at different times. So for example, up top, you see a fuel cell that can run on hydrogen as well. And then that can power things, for example, later in the evening when solar isn't available or when wind isn't available. Or it can go into hydrogen vehicle, or as we've discussed, potentially even into the natural gas pipelines. So using kind of all the tools and tricks and technology we have will really help kind of bridge the gap and hopefully flatten the duck curve, if you will, so that we can lower the carbon footprint of the planet and the world and the universe. And I think that's all I've got. Thank you.
Jared, thank you very much for that presentation. And next up, I'm excited to introduce Angelica Chow, who is going to give us a sort of case study, if you please. I'm excited. Angelica is one of two people that I've been up on a roof installing solar with. And so I'm excited to hear her presentation and see the other side of what she does as a brilliant electrical engineer. Angelica, the floor is yours.
All right, thanks, Troy. So today I'll be talking about a healthcare microgrid project at a hospital in Ontario, California that we are currently working on. I actually saw someone in the Zoom chat earlier commenting about cleaner emergency backup power, moving away from diesel tanks. And that's pretty much exactly what we're trying to do with this project. Currently, many hospitals are still equipped with diesel generators. So in light of decarbonization, can we ease off of these diesel generators and move towards microgrids instead and use carbon-free and carbon-neutral power sources? And so a couple years ago, Mazzetti worked with Charged Bliss on a California Energy Commission grant-funded project. We designed and engineered a renewable microgrid consisting of solar and battery storage at a hospital in Richmond, California. And with this project, we were able to provide backup power to the hospital's life safety loads. And now with Ontario, it's also a CEC grant-funded project. And we are trying to demonstrate that this microgrid can provide backup power to the hospital's full essential system. So we're tying into the critical equipment and life safety branches of power. Similar to the last project, we are also working with OSHPD, California State Review Agency for hospitals, and we're trying to ensure the compliance of this microgrid with OSHPD. We can go to the next slide. A little bit more information about the site on Ontario. Ontario is located in Southern California, so it gets a lot of sunshine. It's close to the desert, so the facility is planning on installing 2 megawatts of new solar panels with 9.5 megawatt hours of energy storage in the form of batteries. There is an existing 1 megawatt fuel cell system that we will be including, as well as another source of the microgrid. And so therefore we're looking at about 3 megawatt of backup power. And you can see the locations of the solar panels and batteries and fuel cells on the site plan. And on to the next slide. Here is an example of the normal single line diagram. Unlike diesel generators, the beauty of this microgrid is that the fuel cells, the PV, and the batteries can run in parallel with the normal utility power. In this case, it's Southern California Edison, and it will act as a supplemental power source. And we're hoping that this can help the hospital with achieving cost savings and energy usage. And in the next slide, we are showing the emergency single line diagram. So basically, long story short, when the normal power is interrupted, the generators will automatically start, and then the fuel cells, PV, and batteries will connect to the microgrid bus in parallel to the generators. And with the additional power coming from the microgrid, the goal is for the generators to start easing off of the emergency bus. Therefore, using less diesel generators and more of these renewable and carbon-free sources. And we're hoping that with the success of this project, that this will be a big step in proving that hospitals can move away from diesel generators and instead move towards microgrids with sustainable energy sources. And my case study isn't too long, but that's basically all I wanted to say about the microgrid project.
Perfect. Angelica, thanks so much for that succinct presentation. It brings us to a point where we can start to put our minds together. So panelists, we have questions for you and hoping that you'll engage in a robust discussion. Again, the purpose here is to share ideas and barriers that might help us to decarbonize healthcare. And I'm going to ask the first question. And indeed, I'm going to share my screen again. And so panelists, we have this case study that Angelica so expertly presented to us. To my knowledge, this particular one is not using hydrogen, but we've had a lot of conversation on this call about hydrogen and the hydrogen economy. So the question is, this is a conceptual model. What would it look like to include hydrogen in some way, shape, or form as part of this microgrid? So what would it look like to include hydrogen as part of this microgrid? Just to get the ball rolling, I'm going to ask if Tom will answer that question first, and then we'll hear from others who want to chime in. But Tom, what would it look like to include hydrogen in some way, shape, or form as part of this microgrid?
Sure. So as I mentioned previously, hydrogen can be used as a full or partial fuel source for fuel cells, and in our case, solid oxide fuel cells. So off to the just to the left there, where you see the fuel cells, that is probably presumed to be a natural gas feed, but that could easily be either a 100% hydrogen feed or a partial hydrogen feed, which is something we think some customers are going to be interested in. Due to the relatively high price of hydrogen right now and relatively tough distribution of it, some customers might start with a smaller percentage of hydrogen and kind of blend that in with the natural gas. So that is one way that's the easy way, from my perspective, of introducing some hydrogen into this diagram.
Great, thanks, Tom. Others on our panel?
Yeah, this is Sailesh. Yeah, I mean, I agree with Tom. A solid oxide fuel cell will run on hydrogen with minor modifications in the balance of plant, and there should be no problem. Yeah, so you could run either on 100% hydrogen or a blend of natural gas and hydrogen, depending upon your need.
Yeah, we've heard in this workshop and in others this idea of this hydrogen natural gas blend. Just to be really explicit, I know it was mentioned today, but what are the prospects for blending hydrogen and natural gas in our current distribution infrastructure? Again, I know we commented on it earlier, but I want to make sure that everybody's clear on that. What are the prospects for that?
I mean, this is Jared here. It depends on what you read. Over in Europe, they're transporting and blending anywhere from 5 up to 30%. Some literature that you see in the United States, some research, when they look at the material sets, recommend no more than 20. So I don't think that there's a firm number today on what is an acceptable blend, just on what could the existing infrastructure handle. But then the uncertainty is blend downstream. When you look at residential, what can those appliances accept? So there's what could the infrastructure handle, but then what is the downstream blending? But right now, I don't see anything more than 30%, just from experience.
Great, excellent, Jared. Thank you for that. So if we're talking about, let's say, 30% to 40% maximum blend, how in the short term, in the midterm, in the long term, would we go about getting hydrogen to this site to power a fuel cell? The hydrogen fuel cell that we just imagined. And that's for everybody, not just Jared, but Jared, if you want to, you can go ahead.
I mean, just, I guess the easy answer is your hydrogen generation station, really making it as close proximity as you can. I guess on one stance, would it be practical to assess, can you get a dedicated hydrogen line? Would be the easiest way. Is that the most cost effective initially? So it really depends on your hydrogen source, the location and proximity to the hospital. Because if it's close, then there's the hydrogen blend's not an issue. You can have a dedicated line. But then if it's further away, I guess it really comes down to the LDCs and the infrastructure itself, the transportation.
Great. Other thoughts on that question? And just as you're thinking, panel, about to answer, I want to highlight that I've asked the first couple of questions, but it's open to everybody. You can type your questions in the chat, and Jessica is actually going to represent our audience. And so she's going to join into the conversation and pull some of the questions that you've asked, either now or earlier in the presentation.
This is Alex. Just to add on to what Jared said, ideally for a fuel cell system, what you would want is an electrolyzer and a fuel cell, sort of an integrated system that has electrolyzer as well as a fuel cell. And so when the electricity is available, you could make hydrogen using the electrolyzer, store it somehow, and when on site, and when the electricity is not available, you could then use that hydrogen to run the fuel cell. That would be a good, I know, short-term application.
Right. Following up, Jessica, would you like to ask a question on behalf of the audience?
Sure, and we have several questions, so we'll try to work through them as much as we can. So kind of on a similar vein, there was a question around specifically how, and maybe Jared, we might start with you, how will we address the embrittlement of pipes when transporting hydrogen?
Can you say that? How would it be addressed? I missed that.
I think it's the embrittlement. I think I'm pronouncing that correctly.
The embrittlement, yes.
Of the pipe.
Yeah. Really, that comes down to, ideally, you would like to use the existing mechanical infrastructure. So that comes down to advanced liners. We are making advanced liners, and there's new polymer materials that you can develop. Actually, it's to curb methane leakage in old pipelines, and they're very resistant to hydrogen. So ideally, you want to have advanced liners. But then the challenge, I just want to be realistic, that comes down to is the application of those liners under older, tortuous pipelines. So yes, the liners can be very good, the new polymers and new materials to retrofit those lines. Now that's very doable to come up with new materials, but then mechanically getting those installed within the existing system will be a challenge, but it's doable. You would want to retrofit. It's not really practical to say we're going to replace the entire 2 million miles of pipeline just for hydrogen.
Great, thank you, Jared. I think it is somewhat difficult to hear you, but hopefully the audience captured that. And if not,
Okay.
we are capturing it. We'll follow up in the recap.
Sorry
No
about
worries.
that. Okay.
No, you're fine, Jared. Thank you. Let's shift gears a little bit. Troy, feel free to interrupt me at any time. I want to address it. I think this has come up in a number of questions, but maybe not explicitly this. We've heard from Tom from Bloom regarding the fuel cells currently in operation and the research from our folks at the DOE. So maybe, Tom, if I could ask you first, what are you seeing that is making the Bloom fuel cells a reality today? How's that possible? And I definitely want to give time for Jared and Shailesh to respond to that as well, if that's okay.
Okay, unmuted successfully.
Are you there, Tom?
Yeah, I'm
Okay.
there. I'm sorry, could you rephrase that question for me a little bit?
Sure, it wasn't completely clear. I think, so we've heard about the Bloom fuel cells currently in operation today, as I understand it. And we've looked at some of the research now that was shared from Shailesh and Jared around the Department of Energy, what the research they've been doing. And it seems like the technology that you're using today is operable, though maybe not mainstream. So I guess I'm asking a difficult question, Tom.
Sure.
How is it possible today to do what you're doing today? How's that?
Well, yeah, no, that's fair. And I definitely want to hear Shailesh's view on this at all, because we're coming at it from different perspectives, but I hope with the same goal. So we've been in, trying to productize fuel cells, since the early 2000s, and have, successfully done that with a dedicated kind of purpose team. So we have, kind of pushed forward in that regard, and we have a lot of production deployments, and we're definitely a production quality, commercial quality product that is, very reliable and has been for some point in time. We're kind of on our third generation. I'm not trying to make this a sales pitch, please don't misunderstand me, but it's definitely a very real product in some situations. It doesn't fit in all situations. As I mentioned before, there are states that have a lower cost of electricity, and those are obviously more challenging from a financial perspective. But as we go forward, we really see kind of the way we want to progress and the way we want to see the industry progress is one towards a cleaner one that uses less natural gas, or I saw for the conversation, methane as a fuel source, use less of that, to use more hydrogen, to participate in that hydrogen economy more efficiently. And we're even looking at carbon capture as well. So even if you need to use, I should say, a natural gas as a fuel source, if you can capture the carbon from the output and then later either use that for commercial purposes or sequester it, then you're kind of running, negative carbon. So that's a whole bunch that I hope to answer the question. And if not, I'd like to hear what Shailesh has to say.
No, I certainly cannot comment on Bloom because they're not part of our program, and I'm only familiar with Bloom as what's on their website. So clearly, I will refrain from commenting on Bloom. But as far as what we are funding, we as I clearly mentioned, ours is an R&D program and first of a kind prototype development program. We are looking at lowering the cost of fuel cell system, meaning at the end cost of electricity, and improving the reliability. And we are spending the R&D dollars right now such that when we develop our first of a kind with maybe 2 or 3 iterations, they meet a certain cost target, which then can be lowered by making in volume. Okay, so that's the target for for the DOE program. And where we are, as I clearly showed in one of my slides, the first of a kind 200 kilowatt system that was funded through DOE had a degradation rate of about 1.5% per 1,000 hours, which is good in terms of where the R&D is, but it's still quite high. Our ultimate target is 0.2%, one order of magnitude below where we are right now, such that the stack will last for 5 years. Our target is, in order to meet the cost target of cost of electricity, among other things, one of the things that has to be there is the stack has to last for 5 years. And clearly the projects that we are funding right now are not there yet.
Jared, I don't know if you had anything you wanted to add to that.
No, I don't.
Okay. Okay. And actually, that's a great segue, Shailesh, if you don't mind speaking maybe a little bit more to what happens to the fuel cell stack at end of life. And specifically, someone asked, are the rare earth materials recoverable?
No, because they are fully sintered, and so it's a ceramic product. Okay, so a fuel cell, basically the rare earths are used in the fuel cell. And so as a part of the cathode, as a part of the electrolyte, and even as a part of the anode, there are at least 4 or 5 rare earth elements, yttrium oxide. So yttrium is used. Scandia is used in the electrolyte. It's also used in the cathode. Lanthanum is used in the cathode. All these things are basically baked. They're ceramics, so they're baked at a very high temperature. And today there is no program that is dedicated to the recovery of rare earths after the end of life. And I'm not sure if it may be technically possible, feasible, but probably not economical to recover the rare earths from the diseased fuel cell.
Thank you, Shailesh. Switching gears for just a moment, Jay, you presented at the beginning the grid, and then we talked about how we're thinking outside of the grid as well. One of the mega trends that I'm excited about is distributed energy, distributed generation, and what microgrids can unleash as it relates to that. I'm curious, how are you, or how are utilities in general thinking about distributed energy and about business models that might be helpful for the distributed energy producers as well as you? I know there's a lot in there, but I just want to start hearing your thinking about distributed energy and where there's synergies for users like hospitals.
Well, this is going to be a very California-centric answer to that, but one of the major issues we have is wildfires and cutting off customers from their power because of our lines creating a hazard for wildfires. And so distributed energy has become moved to the forefront of our work because of that. And so ideas like putting fuel cells in facilities and all of that goes with that whole idea of being able to decentralize our power. The way I always think about it, as not an electrical engineer, is that the system used to be like your circulatory system, where you had a heart in the middle and you kept going out to smaller and smaller lines, capillaries. But now we're pumping the other direction from capillaries. The power is going back into the grid, and our whole transmission distribution systems being re-looked at by the fact that we have all these generation sources, like not so much the fuel cells right now, but solar power and all of that. And so it becomes a big issue for us regarding islanding and being able to maintain critical power if there's a fire. Angelica, don't worry about your site. I was the mechanical engineer at record on that site, and it's in no danger of fires. So don't worry about that for you. But that's a big Again, it's a big thing, decentralizing power. And the other thing is, as somebody, one of the other presenters brought up, the duck curve. We have all this power right now until the sun goes down. And, trying to ride through that 4 to 9 o'clock period, things like storage, battery storage, fuel cells. So, I mean, even if you go back to some of the systems that were presented here where, conceptually generate hydrogen using fuel cells during the day and then turn around and reusing that hydrogen to generate electricity when solar isn't really out there. Those are areas that we look into. If that helps the question at all, Troy.
Okay, that's perfect. And that leads to a question about that duck curve, or the idea that there's a glut of energy in the daytime. So in theory, we could use electrolysis to create hydrogen and store it locally, and then use it kind of on the other side of the duck curve when there's greater demand and not as much supply. Why isn't that happening today? What are the barriers to that happening today? For example, at the site Angelica presented, or somewhere else. Salesh, Tom, Eric, what are the barriers?
Well, I mean, this is Jared. One key barrier, it's not really a barrier, it's cost. So if you take the extra power you have today during certain times and you want to use electrolysis, which would be your greenest, your lowest carbon, I think you're still $4 to $5 per kilogram of hydrogen. And then you have to store it. So your storage facilities on the surface or even subsurface are still under development. It's not completely commercialized today. So the cost of electrolysis and the storage is not, we still have development to be made. So that's why it's not done today. That's my opinion. This excess electricity of converting, but that's what we're interested in, is using that to generate hydrogen for storage as a low carbon energy source when it's needed.
No, it's an interesting point and a good question, and certainly appreciate what Jared said, because if you try to answer that question, don't include cost, you're not paying attention. It's definitely a big factor. Right now, I mean, if you think about kind of where the renewable energy resources are that people would like to run electrolyzers from, there are wind farms and solar facilities that aren't necessarily, especially in an urban center, there's room for them even. So there are some costs in space in kind of matching the generation of the electricity, the renewables, along with the consumption of it, and there's some inherent distance there.
We have just a couple of minutes left. This has been an awesome conversation. Was someone just about to jump in on that one? And if not, I'll turn it to Jess to ask a final question from our audience.
Troy, can I ask a follow-on question?
Hey, Steve, you were unmuted, so you have the opportunity. I can't stop you.
Yes, you can. So, cost, I'm curious about the cost issue, because what we're talking about, at least in California, is wasted solar resources, right? We are curtailing available solar because we have no place to put it. So we've already made the investment in the generation capacity, and we have to turn it off or sell it below cost to other states. So I'm curious why cost would be a barrier to using what's essentially, getting thrown away right now and not producing any benefit.
Right, because, okay, you're right. Assuming you have free power, that's what you're saying, Dora. You still have a cost of electrolysis in that infrastructure, and then the storage, then you do want to turn that hydrogen back into electrons on demand. Now, turbines can accept it, but then you're getting into the infrastructure, those turbines and stuff. So you're right. On certain locations, assume free power, that's a significant benefit. So it's not 100% cost. It's these other factors of safely storing it, and then looking at that intermittent turbine, that power generator or fuel cell.
Thank you.
I think
Great.
just a quick add to that is that, we're concentrating a lot on batteries right now to be able to take care of the fact that we do have that surplus of people who don't know. On spring days, probably like today, spring and fall days, we have a surplus of solar power on the grid. And so we are we are, dealing with batteries and putting batteries in to be able to store that power to get us between 4 and 9 p.m.
Well, let's give a virtual round of applause to our panelists. This has been an awesome session. You're probably thinking to yourself right now, we just scratched the surface, and we could have had an hour-long presentation from each of these folks and a 2-hour conversation. You are absolutely right. The purpose here is just to get us started, right? We're creating a community that's coming together and sparking our imagination so that we can unleash and understand the potential and the challenges that will hinder us from reaching that potential. The conversation doesn't have to stop here. Right now, you can go to decarbhealthcare.com and continue this conversation. In the next couple of weeks, as the workshops wind down, the conversation on decarb healthcare will pick up intensely, and your ideas, your experiences, and your initiative will help move this entire movement forward. Thank you all so much for joining. We have another workshop in 2 weeks, which we're excited about. It's code word decarbonized. We're going to dive into the code as a barrier and as an enabler for decarbonizing healthcare. We have a great lineup for you and are excited to see you there for a great conversation. Have a great day, everyone. Bye-bye.
Thank you, Troy.
All right, thank you.
Thanks, Troy. Thanks, everyone.
Thanks, everyone.